Okay, hi everyone. Welcome to the Graphs of Matroids seminar. Today we're going to have two speakers, so a talk in two parts. The first speaker is Sophie Spirkl from the University of Waterloo, and I'll let her get into it. Go ahead, Sophie.
All right, thank you for inviting me. Thanks everyone for coming. So I'm going to talk for the first about 30 minutes or so, and I'm going to tell you a counterexample to a conjecture that we're not entirely sure where it came from. It seems to have been around for a while, so I decided that the title is a counterexample, and then the second talk will be a second counterexample. And this is in joint work with Alvaro Carbonero, Patrick Hump, and Ben Moore. So the counterexample is about graphs with large chromatic number, and let me first tell you the definitions that I always say at the beginning of talks. If we have two graphs G and H, then we say H is an induced subgraph of G if H can be obtained from G by deleting vertices. So as opposed to subgraphs, you're not allowed to delete edges except when you delete one of their ends. And if H is not an induced subgraph of G, then G is H-free. And here's my favorite example. If we have this graph G, this is an induced subgraph, and this is not. So the two parameters of graphs that we'll care about here are chromatic number and clique number. The chromatic number is the smallest number of colors you need to color the vertices, meaning you assign the vertices numbers 1 through k with the property that adjacent vertices should get different colors. And then the chromatic number is just the smallest number of different colors you need to make that happen. And the clique number for the graph is the size of the largest set of vertices that are all pairwise adjacent. So again, going to my favorite example for this graph G, we can see then the coloring with red, blue, and green here is a 3 coloring. And in fact, that's the best you can do for this graph, and clique numbers 2. And so there are a lot of questions about, suppose that I give you a graph and its clique number is small and its chromatic number is huge, then what can we say about it? Where does it come from? And this conjecture, which I'll tell you more precisely in a second, says if G has huge chromatic number and sort of small clique number, then it contains a triangle-free graph that still has pretty big chromatic number. So it says large chromatic number, if I have small clique number, actually comes from a triangle-free graph with sort of big chromatic number. And more precisely, if I tell you a bound on clique number and a chromatic number that I want to get in a triangle-free induced subgraph, then there is a chromatic number I can prescribe for G, such that if I have G and it has chromatic number at least that number n and clique number at most my fixed bound k, then some induced subgraph H of G is triangle-free and has chromatic number at least R. So for any fixed bound on the clique number, if I pick a graph with sufficiently large chromatic number, it has a triangle-free induced subgraph that has as large a chromatic number as I want to. And this conjecture, as far as I know, has been around for a long time. It's sometimes attributed to Esperet, but I asked him and he said it existed before he stated it. So this is a conjecture that we disproved. And part of the motivation for trying to prove it is that it's true if we don't say induced here. There's a beautiful proof of Rödel's that shows that if I just ask for H to be a subgraph, then this is true. But for induced, it's false, and it's sort of false in a very extreme way, which is even if I just look at k equals 3, then there's a counterexample. So if I look at graphs that have clique number at most 3, then within there I can find graphs with arbitrarily large chromatic number, but every triangle-free induced subgraph has chromatic number in most 4. So then this proves the conjecture, because even when k is 3, when r is 5, I am out of luck for this. Okay, and I'll tell you the construction. And the construction is first based on a construction of Zykov, which is used to obtain triangle-free graphs of large chromatic number, which seems sort of counterintuitive for this purpose, but it will make sense. And so how it's defined is we start with D1. D1 is a single vertex, and then Dn is defined inductively. And this is a digraph, which will also make sense in a second. To define Dn, I'm going to take n-1 copies of Dn-1. So here they are, and I'm labeling them with a superscript to distinguish the different copies. So here's one copy of Dn-1, here's another, and I'm making n-1 of them overall. And now I'm going to add new vertices. And the rule is for every transversal, meaning for every choice of one vertex in the first copy, one in the second, one in the third, and so on, one in the last, I add one new vertex that corresponds to this transversal, meaning this choice of one vertex in each copy. And I'm going to put in edges at this vertex from the vertices in my transversal. So VT is a vertex with no out neighbors, and it has exactly these n-1 in neighbors. And therefore, the number of vertices of the form VT I add is, well, the number of transversals. So it's the number of vertices in Dn-1 to the power n-1. So D1 is this, as we said. For D2, I just put one copy of D1, and then there's one transversal, so I get one new vertex. For D3, I'm supposed to put two copies of D2, here they are. And now there are four ways to transverse, which is top vertex, top vertex, top vertex, bottom, right? And so here we have a vertex whose neighbors are top vertex, bottom vertex. Here's top vertex, and here's top vertex, bottom vertex, and so on and so forth. So that's D3, and they keep going like that. And so they're clearly triangle free because for this vertex, its neighbors are not adjacent to each other, but that's not really important for us. But the chromatic number of Dn is at least n, certainly true for D1. And now for Dn, if we assume that I need at least n-1 colors to color the n-1, we can show that n-1 colors are not enough for Dn, because if there was an n-1 coloring of Dn, I would use all n-1 colors here, and I would use them all here, and I would use them all here. So I could pick a vertex in here, which is colored with the first color, a vertex in here, which gets the second color, and so on. A vertex in here, which gets the n-1 color, and then for that transversal, its neighbor sees all of my available colors. So he has no color left, which means contradiction, we can't color with n-1 colors, so chromatic number goes up, and that's one of the well-known ways of making triangle-free graphs with large chromatic number. The second thing about this graph is that if I look at two vertices u and v, then there's at most one directed path between them. And this was proved by Kierstead and Trotter, who used this construction as a basis in a similar way to ours to prove something else about graphs with large chromatic number. But for any two vertices, there's at most one directed path between them, because certainly if you assume it's true in here, if you look at all the new vertices we added, they don't have out neighbors, so they're not going to be in the middle of a directed path. They will only be at the end. So if I have two vertices and a directed path between them, then I can't have one of them be here and one of them be there, because the path would contain in the middle one of my transversal vertices. So the only two things I can do is maybe they're both here, or maybe one of them is here, one of them is out there, because the vertices that are transversals can only be the very end of the path. And so if they're both in here, I can't use any of my transversal vertices, so the path must have been there before there was at most one, so there's still at most one. And if I'm going from a vertex and a copy of Dn-1 to a transversal vertex, then I'm not using any of my other transversal vertices. So the only way to get into this graph is to use the one edge to my one neighbor in that copy. And then, well, the path from wherever I was to that in neighbor is unique by induction, right? So this shows that if I look at this graph, for any two vertices, there's at most one directed path between them. And in particular, it implies that this graph is acyclic. But it also gives us nice things we can do with this. Kierstead and Trotter then said, let's make two vertices adjacent if they have a path between them and it's odd. And in our construction, we're going to do that except 1, 3. And then later you will hear what happens if we change from 2 to 3 to any prime. But here are the rules. I have dn, which is the Zykov graph with directed arcs. Now I'm going to take the same vertex set and I will add edges according to two kinds of rules. For two vertices, if there's a path between them, then there's only one. And if its length is 1, 1, 3, put a blue edge in the direction of the path. If it's 2, 1, 3, put a red edge in the opposite direction. So for two vertices in dn prime, they're adjacent if there is some path between them in dn, a directed path, and its length is not divisible by 3. And which way they're adjacent depends on what the residue of the path length is. And so first, blue edges include edges of dn, because if u is adjacent to v in dn, that's the path of length 1, which is 1, 1, 3. So dn is a subgraph, not induced, but a subgraph of dn prime, and so dn prime has big chromatic number. Also, we never get edges between two vertices in both directions, because I put an edge between them if there's a path, and that path is unique, and so its length is either congruent to 1 or 2 or 0, 1, 3. So I either get this edge, that edge, or neither, but I never get both. So this is a simple digraph. For every two vertices, there's at most one arc between them. And then there's one nice property, which is that paths concatenate. So if I tell you that in dn prime, I have a red edge from u to v and a red edge from v to w, that means somewhere there was a path of length 2, 1, 3 from w to v, and a path from v to u, also of length 2, 1, 3. And we said dn is acyclic. So if I look at these paths and concatenate them, that concatenation is a walk from w to u, but in fact, it's a walk in a cyclic graph, so it's just a path, which means putting these two gray paths together, I get a path from w to u of length 2 plus 2, 1, 3, so it's a path of length 1, 1, 3, right? The point is, because there is no directed cycle in the end, and because if there's a path, there's a unique one, these definitions have to be consistent with each other. And if I have two red edges in a row, they tell me that I get a certain path between the ends of that two-edge red path. And I can read off its parity because I know how long a path the red edges correspond to. So if u is red adjacent to v, v is red adjacent to to w, then I get that w is blue adjacent to u. And there's symmetry. If the same thing happens with blue and red switched, then I have a path in dn of length 1, 1, 3 from u to v, and a path from v to w of length 1, 1, 3. So from u to w, I can concatenate them to get a path of length 2, 1, 3, which tells me that I should put a red edge here. So what have we done so far? dn prime has big chromatic number because it contains dn. And now what I should show you is A, that dn prime has small clique number, and B, that its triangle-free induced subgraphs have small chromatic number. Let's first argue about its clique number. And here is a bunch of cases that are actually, for the most part, all symmetrical, but it's very hard to convince you of that quickly, so I drew them all. So I claim that in Dn prime, we don't have a triangle of edges that don't form a cyclic triangle, but rather a transitive triangle like this. And suppose you have such a triangle, then we can look at the colors of the edges. There are 8 cases, and here they all are. And in each case, there's something wrong with this picture. If all the edges are red, then we know something is wrong because we just said if there's a 2-edged red path, then there should be a blue edge here. Contradiction. And likewise, if they're all blue, then something is wrong for the same reason. If they don't all have the same color, then I have a vertex that either has 2 in edges or 2 out edges of different colors. And if I have edges that are both in edges or both out edges and they have different colors, then I can put them together as pans. Right, just looking at this example, here W has a blue in neighbor and a red in neighbor, but blue means there's a path of length 1 from U to W, and red means there's a path of length 2 from W to V. So from U to V, the distance is 0 mod 3. But then they're not adjacent. Those are the rules, right? There's only one path length, but if it's 0, then they're not adjacent. So this edge is a problem that doesn't exist. And in each picture, there are 2 such pans you can concatenate to show that one of the edges is actually not present. So we don't have a triangle like this. But if you look at a digraph and you have 4 vertices that are all pairwise adjacent in some direction, then there is a triangle like this because there are 6 edges, so the average out degree is 1.5. And if you look at a vertex U with 2 out neighbors, then those 3 vertices make a triangle, which is not a cyclic triangle. Which means, since we don't have such a triangle, we don't have 4 pairwise adjacent vertices, so the clique number in the underlying undirected graph is at most 3. Good. We've proved big chromatic number. We've proved small clique number. Now let's prove that Trianglefree induced subgraphs are 4-colorable. That's actually easy for the following reason. If you look at any vertex, so let's look at H, an induced subgraph of Dn prime with clique number 2. Then we don't have triangles, any kind of triangles. Now, that means no vertex has both a red in neighbor and a red out neighbor, because we said just a second ago, if we have a 2-edged red path, then there would be a blue edge here, but we're supposed to be triangle free, so that doesn't happen. And likewise, nobody has a blue in neighbor and a blue out neighbor, because if there's a 2-edged blue path, then there would be an edge here, but H is triangle free, and that's not allowed. Right, and here it matters that we're talking about an induced subgraph, so these arguments carry over from Dn prime to H. So that means in H, each vertex either all its in neighbors are, all its blue edges are in neighbors, or all its blue edges are out neighbors, and the same for its red edges. So each vertex falls into one of 4 categories. All of the blue edges are in edges, and all of the red edges are in edges. All of the blue edges are in edges, all the red edges are out edges. And all the blue edges are out edges, red are in, or all the edges are out edges. Right, there's no other case. There might be vertices that only have blue edges, but each of them fits in at least one of these groups, and just group them into one of the groups in which it fits. This is a 4-coloring, because you look at each group and you say, could there be a red edge with both ends in this group? Well, no, because in this group, all the red edges are supposed to be out edges, so this vertex does not belong here. And likewise, no group can have a blue edge. So this is a 4-coloring. Right, another way to say it is, if you look at red edges only, you don't have a 2-edge directed red path, which means among red edges only, the graph is bipartite. So you can partition into two and kill all red edges. And then you do it again, partition each part into two more and kill all blue edges, and that's okay. So every triangle-free induced subgraph has chromatic number at most 4. That's it. We've already proved everything. So let me tell you one more question and then finish with this part. So these are the bounds we get. We have a graph with any arbitrary large chromatic number and its clique numbers 2. Its clique numbers 3, and any triangle-free induced subgraph has chromatic number at most 4. There's a result of Scott and Seymour that says we're almost best possible here, because they prove that if I have bounded clique number and large chromatic number, I get an odd whole, which is an odd induced cycle of length at least 5. And those are triangle-free graphs that have chromatic number 3. So they showed that for any k, if chromatic number is big enough and clique numbers at most k, then I get an induced subgraph H, which is triangle-free and has chromatic number 3. So there's only one gap here between, is it actually 3 or is it actually 4? That's still open. We checked for our construction, and it is actually 4. It contains triangle-free graphs that require 4 colors. But this is still open. It's tight except for this gap of 1. And that's all I wanted to say. Thank you, and stay here for the second talk. And if you have questions in between, we can do some quick questions.
Yeah, thanks, Sophie. Yeah, I'm not sure. I hadn't decided if we were going to do applause now or later, but maybe we'll do it at the end. If anyone has a quick question, we could do that for a minute or two, and then switch over to James.
Yeah, I have a quick question. So there's 3 or 4 questions. You said for your construction, what if you use different starting graphs with large chromatic number, but with the same orientation property? Does it fail for all of them? Is it just due to the way you add the edges? Or so if you started off with, say, tut graphs instead of these ones, does it make a difference? Is it just the edges you add that are creating the chromatic number 4?
I mean, we start with a single vertex, so yes, right? Any graph would contain that.
No, but if I have a graph with large triangle-free graph with large chromatic number, if it can be oriented so that everything has almost one path, and then I add the edges in the way you've just described, are these constructions always going to have chromatic number 4? Is it?
I see. I don't know. We just checked for this one that you contain a certain orientation of C5, and then you get the zygo graph of C5, essentially. And so, but yeah, that's a good question. I don't know.
I may add something, maybe. I had a very similar question. I just wanted to point out that instead of starting with this orientation of Zykov, you might start with the burning graph that has exactly the same property of unique path. So maybe it would be worth trying, and I don't know if you didn't think about them.
We didn't try that yet, but we should. Yes, thank you.
All right, thanks again, Sophie. James, if you want to try to share your screen,
Sure.
We'll get going. Awesome. Okay, and James, whenever you're ready, go ahead.
Hi, thank you. So this is joint work with Marcin Biąski and Bartosz Wolzak, and this is following on from the new ideas and constructions in Sophie's talk. So first, the definition that was touched on, but we need for this talk is Kaiboundness. So we say a class is chi-bounded if graphs in the class with bounded clique number are bounded chromatic number. And we can look at this function f, which is the function bounding it, as the chi-bounding function. So at the end of Sophie's talk, we already saw one class, which is chi-bounded, which is these graphs without an odd hole. So if you don't have an odd hole, then you have chromatic number at most about 2 to the 2 omega. So it's double exponential boundaries. It's a big bound, but in terms of chi-bounding functions you get out of a lot of proofs, it's actually not so bad. And we saw this is close to tight in terms of this is triangle-free induced subgraph chromatic number at least 3, because their breakthrough result was this construction of K4-free graphs with large chromatic number and their triangle-free induced subgraphs a chromatic number almost before. So Sophie's already talked about this result, but I'd like to say a few things about it as well, because I really don't think I can overstate how important I think this result is. Like, I think it's really a big breakthrough. So it disproved this conjecture that if your triangle-free graphs had bounded chromatic number, then you're chi-bounded. So if that was true, that would have been amazingly powerful, but also a kind of strange thing. If you look at the definition of Kaiboundness, well, the clique number is used right here. Like, it appears in the definition. So you'd kind of expect clique number to, or cliques to be important for a definition of Kaiboundness and Kaiboundness in general. What that conjecture is saying is that they had nothing to do with it, and that everything is reduced to a triangle-free case, which it's a silly sounding thing, but before this breakthrough, we had no example to say that wasn't true. And that to me really highlighted that I didn't really understand what the definition of Kaiboundness was on some level. And I've worked with Kaiboundness quite a bit now, and what I'm writing my thesis on this year. And it would have been kind of sad if I finished my PhD and couldn't say I felt like I understood the main definition in my thesis. So this is really a breakthrough result, I think. And after seeing this, like, it was very illuminating and everything came together. And now I think I can say I understand the definition. So that's great. So what I'm talking about today is an extension of these ideas from this construction. So we want to extend this in 2 ways. So they proved this chromatic number separation for graphs with clique number 2 and 3. So you can have large chromatic number with clique number 3, while your clique 2 subgraphs are bounded chromatic number. So we want to show that you can have this separation between any large clique numbers rather than just 2 and 3. But also we want to examine what kind of chi-bounding functions f we can have. So we want to show that you can have weird and big things here. So what would be a nice property for a chi-bounding function? Well, like with any bounds, you like it if your upper bounds are small. So this double exponential bounds, it's not too bad in the scheme of things, but what you really like is polynomial generally. So let me mention a few polynomial Kaiboundness results from the last few years that I like a lot. So perhaps I'm biased with this first one, but the first one I mentioned is circle graphs. So circle graphs are polynomially Kaibounded, and these are just intersection graphs of chords in a circle. Another one I like is that graph with bounded clique width are polynomially Kaibounded. And another from last year is that if you forbid a double star as an induced subgraph, then you're polynomially Kaibounded. So a double star is a tree with at most 2 non-leaf vertices like this. So these are all results I like a lot, but something that I always thought was a shame was that we didn't actually know for sure that what we had proved with any of these was actually anything special. Like if this is anything that distinguished them from other chi-bounded classes. So there was this conjecture that actually every every hereditary class that's chi-bounded is also polynomially chi-bounded. This would say that actually all these nice polynomial chi-boundness results is just something all chi-bound classes could have. So I don't think anyone really believed this conjecture, but it was still a case of, it was something we frustratingly really couldn't find a counterexample to. So from extending the ideas from this recent breakthrough, I'm happy to say that we can get a counterexample to this. So we can construct hereditary classes that are chi-bounded but not polynomially chi-bounded. And actually we can do quite a lot more than this. So we're able to prove this stronger, slightly technical result, which isn't actually in the paper yet. So roughly what this says is, it says two things. One, we can get this separation between, for chromatic number, between consecutive cliques, no matter how large. The other thing it says is that we can construct classes with arbitrarily fast growing chi-bounding functions. And we can make those chi-bounding functions exactly even, so long as they're big enough. So more precisely what it says, if we have this function going to natural numbers and infinity, we have this condition of f of 1 equals 1, just because fun. Graphs of clique number 1 have chromatic number 1, that's why we have this. And then there's the second condition that otherwise a function f at least, this cubic function, then so long as f. Yep.
I guess it also has to be, I mean, it has to be increasing clearly, but
no. So the way I've defined it, this is for clique number exactly equal to omega, rather than at most. So it doesn't have to be increasing.
oh wow.
It's
That's
weird,
ridiculous.
isn't it? Yeah, so we can jump up to infinity at clique number 4 and then go down to something more normal after that.
Oh
So
wow. Spooky.
It's a strange thing.
Yeah.
So really the only requirement is that our chromatic number we're asking for is not too small at any value for the clique number. Otherwise, we can pick any insane looking thing we want. So I think this is very general, and almost anything, as long as it's not small, that can be a chi-bounding function essentially. Okay. So the way we prove this is essentially we just want to look at a separation between one clique number and the next, one at a time. And we just want to do this in a controlled enough way that now the induced subgraphs with smaller clique number all have bounded chromatic number, bounded by this 3 omega plus 2, choose 3 function. And in that way, this is independent of this n plus 1 clique separation. And by doing each of these separations for n plus 1 in turn, we can exactly choose the value of f of n at each n, so long as our f is always at least this upper bound we have for the induced subgraph with smaller clique number. So this theorem is just a corollary of this one. So actually a much easier case of this is when n's a prime number. So a couple things is first is we actually get a better upper bound for a subgraph with clique number omega less than p, which is just omega plus 2 choose 3 rather than this 3 factor. So this is much easier when it's a prime. And to go from prime to non-prime, I won't talk too much about how you do that, but essentially the non-prime constructions is just subgraphs of other prime constructions. So in some sense, we work our way down by picking a prime that's larger in n, but not too much larger, is how that will work. But I won't talk too much about that. So today I'll just focus on this construction for primes. And already just this construction for primes is enough to make your class, make a chi-bounded class that's not polynomially chi-bounded, because you just do your separation of primes. So a couple of things before I get into this construction is the p equals 3 case is essentially the same as this breakthrough construction we saw from Sophie just now. And the p equals 2 case is essentially the same as this earlier construction where ideas came from, where we're adding in the edges that odd distance. This is essentially the same as a p equals 2 case. Okay. So like with those two constructions, we start with the following lemma. So what we start off with is triangle-free graphs with large chromatic number, so that they have an orientation that's acyclic, and so that between any pair of vertices, there's at most one path between them. And just like with the others, what we do from here is we just start adding in edges between vertices at a certain distance along directed paths. And we do this in exactly the same way, where for our fixed prime p, we're going to add in edges between vertices at distance, anything that's not a multiple of p. So anything that's congruent to something different than 0 mod p. And for simplicity and what I'm going to go through, I'll just fix our prime p to be 5. So if we have this directed path in our example, then we start off by adding in all our 1 mod 5 edges. We've already got the length 1 ones, but there's longer ones. So we add these in. We add in the ones that are 2 mod 5, 3 mod 5, and 4 mod 5. So we're basically adding in all of them except for these ones that would be a multiple of 5. Okay, so that's a construction. One property we clearly maintain is that we still have large chromatic number, or whatever chromatic number we picked, because all we're doing is adding in edges. So the bit that's important to examine is that we don't have clique number more than p, and we also need to examine cliques and induce subgraphs. So next I'll look at what a clique can look like in this thing. So say we look at a vertex in our graph and we want to look at a clique that contains it. Then it might look like this. So because of the way we're adding these directed edges along these directed paths in the same direction, our cliques are all going to be transitive tournaments in this case. So in particular, if we clique has a tail vertex where all the edges are outgoing, like this one, say. So say this is the largest clique with this green vertex being a tail. Then there must be a reason we got these edges and found this clique, which is that all these vertices must lie on a directed path from our original construction. So they must lie on something like this, is how we obtain them. And then from looking at this underlying path from the original construction, which might not be in our induced subgraph, but it existed before, we can look at the length modulo p or modulo 5 of the edges in our clique. So for instance, if we look at this edge here, we can see this is of length 4 or 4 mod 5. This blue one here is of length equal to 7 or 2 mod 5. And this yellow one's this length is of 11 or 1 mod 5. So we can keep track of the length of these edges modulo 5. And something we can also just do by convention is say that this tail vertex of our clique, we can just say length 0. It's the starting point of our clique, so it's 0. And we could fill in the other edge lengths if we wanted. So one important thing to notice here is that it's important that these 3 lengths here are all different. Suppose we had 2 that are the same, this yellow and blue were both length 2 mod 5, then we'd look to these 2 vertices and see that actually the edge between them would be of length 0, which is not something we're adding. So we shouldn't actually have this edge, and we wouldn't be a clique if we have 2 of these edge lengths be the same residue modulo p. So because of that, our graph's going to have clique number at most p. There will be no p plus 1 clique because we can't find more than p residues modulo p. So roughly speaking, this is what our clique looks like. We have this tail vertex, the 0 green one, and we have these direct tail directed edges of length being different residues modulo p. So this gives us a type of clique, we could call this. So we could look at the residues modulo p, and the type will just be the residues of the edge lengths on the tail. So we have 0, 1, 2, and 4. That's this type for this 4 clique. Okay, so we need to start thinking about how to actually color our induced subgraphs with bounded clique number less than p. So we're aiming for this omega plus 2 choose 3 bound. So this is how we'll assign a color tree vertex. So we're going to assign a triple A, B, C, or positive integers, so that A is at most omega, B is at most A, and C is at most B. And this will give us our omega plus 2 choose 3 colors. So I'll go through one at a time on how we choose each of A, B, and C. So for A, we start off by looking at a vertex, and we want to look at the largest clique, which has this as a tail. So it could look like this again, say. And in this case, our largest cliques are 4 clique. So we're going to make A equal to 4 for this vertex. So next we need to start thinking about what we're going to give to B. So for deciding B, we again want to look at the maximum cliques, with our tail being this green vertex. But we want to account for when we have more than one maximum clique. So in this case, more than one clique of size 4. And we want to somehow account for different types of 4 cliques with our choice of B. So for now, let's just look at what happens when we have different types of 4 cliques with this tail vertex. So here, for instance, we have two different four cliques coming out of it. And this is how something like that can happen. We could have these underlying paths that at some point split like this. And this can, at some point, let us spread out and have a clique going in two separate directions, or two cliques going in two separate directions. So from looking at these underlying paths again, we can again get edge length modulo p or modulo 5 for each of these. And now I want to look at these two cliques one at a time. So let's look at the left one first. Now this is a for clique of type 0, 1, 2, 4, like this say. So this is one type of for clique we have at our green vertex. So we'll keep track of that for later. This is another type. This time we have something different, 0, 2, 3, 4. So this is what that looks like for residues modulo 5. And this is another type we have. So in this case, we have two types of for cliques that look like this. And now the important bit I want to look at before deciding B is what ones of these residues are within every single for clique. So in other words, what residues is always the length of an edge at a tail of a maximum clique or a for clique. So in this case, it's our 0, 2, and 4 residues that are always the length at a tail of a maximum clique. And this is how I want to choose B. I want B to be the size of this common set of residues of all these cliques. So in this case, because we have these three that are residues of all the four cliques, we choose B to be equal to 3. Okay, so at this point, we're getting close to a proper coloring. But before deciding what C should be, I want to look at what can happen to with neighbors of our green vertex. So say we have our green vertex, which is colored 4, 3, and something to be determined. And we have this these other residues in every for clique, 0, 2, 4. And say we have this orange neighbor with an edge going from orange to green. And suppose for first case that the length of this edge is equal to -1 or equal to 4 mod 5. So it's -1 is 1's not in this set of common residues. Then I want to look what happens with this orange vertex now. Now, next I want to look at a for clique coming out of our green vertex, which doesn't have a residue 1 tail edge length. We can find this because it's not in this common set of residues. So we can find a 0, 2, 3, 4, 1. And it might look like this. So now we can observe that actually, if we had this, then from our orange vertex, we're going to generate a bigger clique, a 5 clique in this case. So this would be a 0, 1, 2, 3, 4 type clique. But then this is either too large clique number to be in a mega size subgraph, mega clique subgraph, or we're going to be coloring this A coordinate as something bigger than 4 because we found this 5 clique here. So this is what happens if the negative of the length between orange and green is not within a common set of residues for green. Okay, so let's look at if it is in our common set. So this time we're looking at -4. So if we have an edge length of 1 between them. Now, let's also suppose that this orange vertex receives the same coloring in the same first two coordinates, so 4, 3. Then I want to start trying to learn what this common free set of residues for orange must be. So to do this, I want to look at what 4 cliques are generated by having this edge going to green. So to begin with, we can look at this triangle, which comes out of green. So we're just taking a 4 clique that doesn't contain 1. So this would contain 4 as well, but we only want to look at the ones not containing 4. So just the 0, 2, 3. Then this is going to give you a 4 clique with tail orange, like so. This is of type 1, 3, 4. And that would look like this. Okay, and now we do a similar thing. We want to look at a different type of clique coming out of green. And this time we'll look at a maximum clique not containing this 3. And again, we also just exclude the 4 that it must contain. So we get this triangle clique of type 0, 1, 2. And that looks like this. And again, this will generate a 4 clique with tail orange here, because we then must have these edges of length residue 2 and 3. And now this gives us a 4 clique of another type for orange, 0, 1, 2, 3. And from here at this point, we can see what our common free set of residues must be. It must exactly be these 3. So 0, 1, 3. So we can, and this is an exact thing. This is exactly determined by the free set for green and this edge length. So actually we can just write this out as an equation, and we have this orange common residue set. This is equal to the green one plus 1, which is our edge length. And this is where the fact that we picked the prime number was important, because we want this to be different to just our green set. So all we're doing to this green set to get to the orange is rotating it around the cyclic prime group so that we have a different starting point at 0. And the fact that we're prime means we can't just send it to itself like this in a non-trivial way. So this is where being prime is important. And actually in this way, we only have one thing we can send it to for each of these non-zero elements. So there's 2 and 4. So if, for instance, we had this other kind of edge, as -2 equals 3, and this purple vertex was also colored 4, 3, then we could show that, again, we have these 3 common residues, and this is just equal to the common residues of our green one plus 3. And actually, this is now how we just pick our color C. There's only at most 3 different kinds of these, according to this orbit of moving the set around this cyclic group. So C can be any of these 3 different values. So with that, we obtain our ABC coloring, and that's our omega plus 2, 2, 3 coloring in the prime case. Okay. So I think there's a couple of obvious questions following this theorem. One is, can you get more chi-bounding functions? So this gives us that provided we don't have any too small value at any point, our function can be a chi-bounding function essentially. But can we get more than this? So in particular, can this lower bound function for f be improved? So we're still looking at seeing if we can color these induced subgraphs any better to improve this. But it might be that through this construction, you just can't do better in cubic for all we know. So it might be that you need entirely new constructions to get this much lower than this. But this is something we don't yet know. So in the other direction, you can ask, well, we know you can't take this all the way because we have this one example showing that our chi-bounding function can't be completely arbitrary. This odd hole result tells us that if f of 2 is equal to 2, then we're chi-bounded. So we can't at any point have a f of omega be too high. So here's a conjecture that would generalize this, which I really think should be true, but I also think we just have no way to approach something like this yet. So here's a conjecture strengthening I'd make, which is for any positive integer, k, if your induced subgraph with clique number at most k, or will have chromatic number at most k, then you're chi-bounded. So in the k equals 2 case, this is exactly the same as the odd hole theorem, because they're triangle-free graphs are bipartite. So this would be a generalization that again says that if your f of omega like way too low, the lowest it can be at omega at some point, then you have some restriction and you're chi-bounded. But I think this would be true, but I just have no idea how you could even go about trying to do something like this. And one more question. So we showed this separation for chromatic number between high clique number. You can go in the other direction rather than going high and higher clique numbers. You can go down. So a natural way to do this once you get down to clique number 2 is to instead start going to higher girth. So girth's the size of your sortless cycle. So here's a question. Is it true that for every positive integer g, at least 3, you can construct graphs with girth equal to g, an arbitrarily large chromatic number, so that their induced subgraphs with higher girth have bound a chromatic number? So this breakthrough Sophie was talking about says that this is true for g equal to 3. For g equal to 4, there's actually a lot of examples that show this. So the prime equals p equals 2 case of this construction also shows it, but also shift graphs and Berlin graphs are also examples which show this for girth 4. But then, as far as I know, this is completely open for any higher girth after then this. Okay. I'll stop there.
Excellent. Thank you so much, James. And thanks, Sophie, for the talk earlier. Let's everyone please unmute and we'll do a round of applause for both of our speakers today. So unmute, I'll count to 3 and then we'll clap. 1, 2, 3. Excellent. And I guess, yeah, does anyone have any questions? Maybe we'll do a few before I end the recording and then we can have some informal discussion.
I was wondering if you've tried making any intersection graphs with this property. Now that you know a class, have you sort of tried to realize it as an intersection graph somehow?
Not tried seriously. So the discouraging thing is that this comes from doing the separation at every clique number. So it makes you think that you shouldn't be able to realize these graphs if you're chi-bounded, because you'd think there's no reason you couldn't just keep going and not be chi-bounded.
Mm-hmm.
But these subgraphs, they might still be part of some natural family. I don't know. It'd be very interesting to have something natural, because at the moment this is just artificial. So yeah.
Last chance for questions. Well, I guess not really. Last chance to have them on the recording. All right, I'll end the recording there. Thanks again, Sophie and James.